In this video I'm going to talk a bit about wave-particle duality and evidence for the fact that we can't consider things necessarily just waves or just particles. So before I get into the experiments which demonstrate these, I'm just going to quickly talk about what we classify as wave behaviour and what we classify as particle behaviour. So the key ones to think about in terms of wave behaviour are diffraction and interference. So in particle behaviour you can start to explain reflection and refraction just as you can in wave behaviour, so they don't allow you a particular way of differentiating between the two, but diffraction and interference are things that are classically only wave behaviour, so it's those two especially that you do experiments to consider to see if something's a wave or a particle. If you want to know a bit more about those in terms of what you would see observationally, I advise you to go look at Unit 2 section on waves, which covers these in a lot of detail, whereas this video is designed specifically around the things in Unit 1 and what you need to know in Unit 1. So that's wave behaviour, so we need to think about the fact whether something can diffract, and once it's diffracted whether they can interfere with each other. So classic things to do with particle theory is talking about one-to-one interaction. So for instance, if light is going to act as a particle, the photons of light would have to be only able to interact with one electron in the atom, for instance. That's one-to-one behaviour, and you'd expect particles to keep travelling in a straight line unless they're acting on a force, so just like Newton's laws suggest. Okay, so let's dive straight in. So the photoelectric effect. Now, just to give some background, the photoelectric effect is when you shine some kind of radiation on a material that has free or delocalized electrons, so most commonly metal type materials. And what you get is actually an electron being emitted. So a photo emission is an electron being emitted. And the current position is we have this equation which we can use to calculate the maximum kinetic energy. So here we've got kinetic energy, that's why it's called EK max, and that's the maximum possible kinetic energy of a photoelectric emission. We've got here something you should recognise from the work on photons, so HF, so you've got a way of calculating the energy of a photon coming into the material, and here we've got the work function. And the work function is the amount of energy you need to cause an electron to be emitted with zero kinetic energy. So it's the minimum energy you need to cause an electron emission. And tied to work function is something called threshold frequency. It's a bit untidy, but I've said it anyway. So threshold frequency, obviously, if you have a minimum amount of energy you need to have an electron be emitted, there's a frequency tied to that photon energy, because obviously they're linked by the Planck's constant. So that's the minimum frequency you need to cause an electron to be emitted from a material, whereas work function, which is what goes in this equation, is just the minimum energy. Okay? So in order to use this equation, you have to make a certain number of assumptions, and we'll come back to whether those assumptions are valid when we discuss wave-particle behaviour. One of the assumptions is you get one-to-one interaction between photons and electrons. So a photon is coming into the structure, it encounters a free electron, and that electron can either absorb it and then be emitted, or it cannot absorb it and nothing will happen. So that's one of the assumptions of it, and that's actually one of the assumptions from particle theory. The assumption is that the electron is on the surface of the material. So this calculation here would give you the kinetic energy if the electron's on the surface of the material and that the surface was neutrally charged, which may not always be the case, but that's why it's EK max, not just EK, because if it's further inside the material or the metal is charged for some reason, you'll get a lower kinetic energy of photoelectric emission in this case. So another thing is that this isn't ionization, which is something a lot of people get confused by. This is a delocalized or free electron in the metal that is being emitted, so this electron's that is emitted is not attached specifically to an atom, it's a free electron. And another thing you need to know is emission is instantaneous. So a photon comes in, electron comes out, or photon comes in, nothing happens. It all happens instantaneously. Another assumption of particle theory. Okay. So in terms of the photoelectric effect, let's have a look at what wave theory would predict. Because after the original period where Newton's corpuscular theory reigned and everyone believed light was a particle, once Thomas Young had performed his slits experiment, the scientific theory shifted to thinking that light was a wave, and it then had to shift back slightly to encounter the various parts of the theory, so whether it was or wasn't a wave or a particle, and had a mesh of both. Anyway, so if light is purely a wave, you'd expect that any wavelength would be able to cause an emission. And the lower energy wavelengths would just simply take longer, because the electron would just keep absorbing the wave until it did have enough energy to escape. So you'd get some electrons being emitted after a period of time. You wouldn't get instant emissions. And therefore, by increasing the intensity of it, basically a way of measuring the amount of energy delivered per second by a wave, you would be able to decrease the time, because obviously it would be receiving energy at a faster rate, so it would be able to emit it more quickly. That's what wave theory predicts. So the idea of photons would predict that only one photon can interact with one electron, and then the electron will either absorb that photon or it will not, depending on whether that photon would allow it to escape or not. So this suggests that low energy wavelengths would never ever be able to cause photoelectric emissions, because they just don't have enough energy, so the electron will not interact with that photon. And it also suggests that if you increase the intensity, so you increase the number of photons arriving at the photoelectric plate per second, you could increase the rate of photoelectric emissions, obviously, because if you get more photons, you can have more electrons emitted. But increasing the intensity would have no effect for the low energy wavelengths, so you can't have two photons absorbed by one electron to give it that kinetic energy. That doesn't work, it's only one-to-one interaction. Alright, so in terms of the experiment that was done to then test this theory, the observations that were made was that low energy wavelengths indeed cannot cause photoelectric emission. So this strongly favours the particle theory over the wave theory, because this is a prediction from particle theory. It was also noticed that some of the photo emissions were a lot slower than the kinetic energy you can calculate from the equation up here, and it was suggested that that was because some of the electrons that absorb the photons are actually inside the structure, they're not on the surface, so then some work has to be done to get them to the surface before they can then escape. They noticed that increasing intensity of the radiation, so the number of photons per second is increased, did increase the rate of photoelectric emission, but didn't actually cause the lower energy wavelengths to be able to cause emission. And they noticed that emission was indeed instantaneous. So this is how we came to the idea of the light waves actually starting to behave back like particles, in addition to the wave-type properties of diffraction and interference that we'll come on to study in Unit 2. So now I'm going to move on to look at particles acting like waves, and there's a few key things to know about this. So there was a scientist called Louis de Broglie. It's written like de Broglie, but it's pronounced de Broglie, as he is, I believe, Dutch. And he proposed that particles have a... oh dear me, that's not come out well. Particles have a wavelength associated with Planck's constant and the momentum of a particle. So that was his proposition. So he was proposing that if waves could act like particles, or why couldn't particles act like waves? And this was his prediction as to what the relationship would be to calculate the wavelength. So in an attempt to see if this was correct, an experiment was conducted called the Electron-Diffraction, and this setup might look a bit familiar to you if you know about Young's double slits experiment. But instead of obviously a source of light, we have a source of electrons called a thermionic emitter. And using magnetic fields, you can actually produce a beam of electrons which you can send towards a double slit. And once they've passed through the double slit, you can have them displayed on a screen. So it's actually a fluorescent screen. So if an electron strikes it, you get a region of a bright area due to excitation and de-excitation. So in theory, what you should see on the screen will tell you if it's behaving like a wave, as de Broglie supposed, or if it's behaving like a particle, as conventional theory would have it. So, prediction of wave theory this time. So if this equation up here does hold, and electrons in this case can behave as waves, you would expect when they pass through the two slits, just like light, that the electrons would diffract and then interfere with each other, producing an interference pattern. So, just like with Thomas Young's double slit experiment, you'd expect these fringes to form because this is a fluorescent screen, so when an electron strikes it, you'd get photons being emitted. So you'd have these regions of light just like in the double slit experiment. So that's wave theory prediction. Particle theory prediction would expect the electrons would go through either slit, and then you'd just get two bands forming on the screen depending on whether they went through the left slit or the right slit. So particle would suggest they didn't diffract particularly and they didn't interfere with each other, they just went through the slits and hit the screen. Okay, so in terms of actually the observations when this was carried out, so this diagrammed at the bottom, you actually have a top-down view, so you're looking at it from above. So you've got the two slits in there, and then you can see how the electrons diffracted. So in the experiment, they found that they did indeed get this interference pattern that you would expect if the electrons were behaving like waves. And what they also found is that the diffraction angle was actually proportional to the de Broglie wavelength predicted by this equation. And what they also found is you'd get these different order bands, just like you did in the double slit experiment. And so then you'd get these equal angles of diffraction forming the bright fringes in there. So this was the experiment that gave evidence to the fact that particles, in fact, did not just act like particles, they could also act like waves. And that's actually an important concept when we're thinking about atomic structure. So rather than thinking of the Bohr model of the atom where everything's regimentally organised into shells, if you consider the electrons as a wave, so you have a cloud of electrons that will snap to the Bohr model when you observe them, that gives you a more accurate idea of the model of an atom, and that's some of the work that Schrödinger and and Heisenberg and those sort of people did to improve the model of atomic structure. But you'll need to go away and look at that. I'm not going to talk about that in this video.